Hi everyone, I'm Professor McBain and welcome back to Chem 100 and welcome back to our lecture series on energy. So let's look at a different situation here. So I start with 250 milliliters of water, but it's already at 100 degrees Celsius, which is its boiling point. And I still have my water on my stovetop, okay? And so it has an opportunity to boil away, and it does, until I only have 250 milliliters left of liquid water. And so that means, therefore, that 200 milliliters, or as we learned a moment ago, 200 grams of water has boiled. So you all know from experience that you have to leave your stove on and you need to continue to supply your pot of water with thermal energy in order to get it to boil. If you take away the energy, it's going to gradually stop boiling and it'll gradually decrease its temperature all over again. Okay, so we definitely know that there is energy required to keep this water at its boiling temperature in order for this much water to boil away. So let's see if this equation is going to help us figure out how much energy is required to make this happen. So let's see, again, the mass that we boiled away was 200 grams. Specific heat of water still hasn't changed. Joules per gram, degrees Celsius. And then, okay, so it was 100 degrees Celsius before, 100 degrees Celsius after. 100 minus 100 is 0 degrees Celsius. So then that means that Q is equal to 0 joules. Okay, that does not make sense. So what's the problem here? The problem is basically that this equation has failed us, and it is all because a phase change has occurred. So what happens is that if you have a phase change, you cannot use Q equals MC delta T. And in fact, you can't even really use specific heat, because specific heat assumes that you even have a temperature change going on. And the same thing here is that it's assuming a temperature change. And what's going on with phase changes is that a phase change happens at a single temperature. So if a phase change is occurring, we can't use Q equals M times C times delta T, because we are going to get the same problem every time, that the lack of a change in temperature is always going to lead us to think that there is no energy requirement. And as we just discussed, that doesn't make sense, and that is counter to all of our lived experience. So we need to come up with a different relationship. So in order to help us do that, I'm going to start off by introducing a new value, which is called the heat of. And there are always two heats of, you'll see. But so the heat of fusion is fancy talk for melting, basically. And there is also the heat of vaporization, which sounds a little bit closer to what it means, which is the boiling process. And these two values, they both have units of joules per gram. And that makes a bit more sense, because in order for something to boil or melt, all that you need is the energy to let the process continue. You need the mass of stuff that you're either boiling or melting, and you need to have already reached the temperature at which the substance melts or boils. But other than that, there is no temperature change that occurs during the phase change, during the melting or during the boiling. So in order to relate these together, this time Q just equals the product of the mass and the heat of either fusion or vaporization. So I'm going to write both of these expressions, but really I want you to think that you only need to remember one of these, and that the subscript here just basically depends on whether you're melting or boiling the substance. So again, we will see examples of how to use this in the Monday lecture, but actually we're going to learn a lot more about it in Chem Activity 11. So I'm probably actually going to hold off to talk with you about this until Wednesday. So it is important to think about where energy for these processes even come from. Yeah, they just generally come from our appliances, but where does that energy come from that powers the appliances? And so one of the biggest sources of energy is from nuclear reactions. Now you may be thinking to yourself, wait, I thought that nuclear power plants weren't so prevalent. I'm not talking about nuclear power plants. I'm actually talking about sunlight. The light and the heat that comes from the sun is really from nuclear reactions that are happening at the sun, which is really cool. And then, of course, you do have energy that comes from nuclear power plants as well. The rest of power plants on Earth use chemical reactions from more conventional fuels. And these chemical reactions, well, really any chemical reaction at all, involves the breaking and making of covalent bonds. But power plants tend to use chemical reactions that tend to give off energy, as opposed to those that require energy to move forward. And one of the most popular ones is, of course, the combustion of a hydrocarbon, such as gasoline or diesel or wood or etc. We're going to talk more about these fuel sources in the future. But being a chemistry class, we need to think even more about why a chemical reaction gives off energy. Because, of course, energy can't be created or destroyed. You might have heard that before in a junior high or high school science class, and that is actually the law of conservation of energy. Okay, energy cannot be created or destroyed. So in these chemical reactions that give off energy, the energy is coming from breaking and making covalent bonds that just happens to have energy left over at the end of that process, and it has nowhere to go but out. And so those are the ones that we're going to focus on. But let's take an even closer look at how breaking and making bonds can result in giving off energy. So first, let's consider this. Do you think that breaking a covalent bond, like this guy, do you think that it would require energy to break this thing? Do you think it would release energy if this thing was broken? Or do you think that it just depends on what kind of bond it is? Well, I won't leave you hanging for too long. Let's take a look. Yeah, so breaking a covalent bond always requires an input of energy. You've got to put energy into this thing. And if you think about it, that kind of makes a good amount of sense. If you consider oxygen molecules just floating around, say, in a forest full of hydrocarbons that totally could combust in the presence of that oxygen, they don't just combust. They require an input of energy before they're going to go through that reaction. So you have to input some sort of energy, some sort of heat or something like that to get the oxygen molecules to break up with each other and then go through that combustion reaction. This isn't just true for oxygen molecules, it's true for anything. The reason being that covalent bonds are really, really strong and really, really stable, and they're not going to break up with each other on their own. They need just a little bit of an input of energy in order for that to happen. Now, the reverse is also true. So not breaking, but forming a covalent bond always releases energy because, again, covalent bonds themselves are stable. Now, you may be thinking to yourself, why does this even matter? Well, let's skip forward to an example problem, an example situation. So I'm looking at the formation of water from hydrogen molecules and oxygen molecules. This is how that hydrogen molecule actually starts out. And this is how the oxygen molecule actually starts out. So they start out as part of a molecule. And so the first order of business, before you can get them to form different bonds, you got to break up those bonds. And so in order to break up those bonds, you need to supply this much energy for the hydrogen molecule and this much energy for the oxygen molecule in order to get them into individual atoms. Once they are those individual atoms, now they have the opportunity to form these new bonds. And that is so nice and so fun and makes them so happy, and so they release excess energy as a result. And in fact, each of those OH bonds releases this much energy, 467 kilojoules. It's not just one hydrogen, one oxygen, and they make one of those. We have to actually obey the law of conservation of mass here as well. Or in other words, we need to still make sure that this reaction is balanced. That's terminology that you all know from week 3 or 4 or something like that. And so you can think of it like this. So I've got 2 of these guys, and so that means that I need to supply 2 amounts of that hydrogen bond breaking energy. And then I've got just 1 oxygen, so I need to supply 1 of the oxygen bond breaking energy. And then I form not 1, but 2 OH bonds per water molecule. And so as a result, that releases 1, 2, 3, 4 amounts of that 467 kilojoules. So if you add up this guy, and this guy, that amounts to 1,370 kilojoules of energy that you have to put in. And then if you add up these guys, that amounts to negative 1,868 kilojoules of energy out. So as a result, 1,370 minus 1,868, that results in 498 kilojoules released. Okay, so just the formation of water from hydrogen and oxygen gas releases energy as well. And this is one of my favorite examples to offer here because this is actually the basis of hydrogen fuel cell vehicles. It's a process that gives off plenty of energy to be used, but without resulting in more carbon dioxide going into the atmosphere. You will see some more practice problems like this. You will get more practice with it on the homework, and then yes, there will be at least one problem that deals with this treatment of chemical reactions and energy on the final exam, because it is important that you understand the basis of burning fuels, putting them through these chemical reactions on the basis of the energy that is required to make and break bonds. While we're on that topic, let's consider the fact that different fuels can release different amounts of energy. This is all due to the fact that different fuels can have different numbers of carbon-hydrogen bonds and hydrogen-oxygen bonds and even carbon-oxygen bonds. And so the mixture of these multiple different kinds of bonds over here, and then them forming carbon dioxide and water, all leads to there being different energy outputs per gram of the fuel that you put in at the beginning. So here's a nice table to show you all the differences, but as you can see, out of all of these conventional but also not so conventional fuel sources, hydrogen actually ends up giving us the greatest amount of energy per gram of fuel, and there's no greenhouse gases emitted as a result of this. Whereas all the rest of these fuels over here, these are all carbon-based. And so these are all going to yield carbon dioxide and water as their products for that combustion reaction. So not only are these less efficient fuels, but they're also going to result in greenhouse gases, whereas hydrogen is nice because it doesn't give you any greenhouse gases at all. So that is why there is a push to improve technology behind hydrogen fuel cells. So now that we have taken a look at how energy comes as a result of the breaking and remaking of bonds on a molecular level, next week we are going to scale it back up to this level where we are going to consider different fuels and where we get them, and we're also going to take a look at which of these fuel sources are utilized the most across the United States. So I look forward to seeing you next week when we start that discussion of fuels. Thanks for joining me.